So now we want to prove regularity lemma. The version, weaker version that, it's equivalent, but in, what was the number? Let me see. Theorem 6.19, summary regularity lemma. We just want to find the epsilon regular partition. We don't care whether this is equitable or not. So how can we actually find this? So let me give you some intuition. Let's make the thing more simple. Let's go down by dimension so that you have some number, say 1, 2, 1, 1.1, 2, 3, 4, 5, 7, 9, 10. So instead of graph, you consider graph is kind of two-dimensional object, and which is not really. I didn't define what mean to be two-dimension, but let's bear with me that. So it's somehow two-dimension, and then this is somehow one-dimension. You have just numbers and nothing else. And here, what you want to do is you want to make a partition so that it gives you some uniformity. So we want to, partition this so that this is 1, 1, say 1.1, 1. So all the numbers here are somewhat close, and 2, 2, 2.1, 1.9, and here 3, 3, 3.1, and so on. So you want to partition them into finitely many so that here the somehow numbers are close. If we want to prove this, then how can we prove this? If we want to do some kind of this partition, one easy way is that once you have certain partition, and then in here, if you have some number which are too far apart, some big number and small number, then you further partition it with a small number and big number. And you keep do that until you get the things what you want. But somehow we have to show that we can do this in a way that at the end we obtain desired partition. So how we want to do it is that somehow, in several times in previously, what you do is you consider certain function depending on this partition. And then you consider the partition which maximizes this function. And then once this is maximized, you have certain property which ensures what we wanted. So basically that's what we want to do. And then what's this function? So how can we take this function? We want to say maximize this function, and then for the maximum partition, we have certain property. So if something is not maximum, then we can always increase. And if this is maximum, we cannot increase anymore, so which gives us what we want. So in this case, if this is somehow maximum or close to maximum, and then if this is not maximum, we can further partition it. That means if we have the numbers here which are far apart, say here 1, 1, 1, 2, 2, 2, which are far apart, then we partition it. And this partition should increase this number. So we have to take certain function. Once we partition this, then this number increase, this function increase. That's what now our goal is we want to come up with a certain function such that before it was certain number, but now we partition further, then this goes up. So that's how we want to come up. When we partition the numbers which are far apart, so here these are kind of uniform, here these are kind of uniform. Before they were together, but now you partition it, then this goes up. So roughly this is the situation. let's make it simple. You have a two number x, y. And in this case, you compute this partition, this function, and then you partition it into 2, and then you compute this. And what happened is that this increase if x and y are far apart. But if x and y are small, similar, then it is small. So this is what we want. So there is one of the easiest way of finding such a function is that you take the average and square. So there are several parts. You take the average and square and then add. So this was before, and then here you take the average and square, and you take the average and square, and then you don't just add it. There are two partitions, so you also have to take the average over the partition. So here you have only one part. So this is average over partition, and each partition you take the average inside and square. And here average inside square and average inside square, and then there are two partitions, so you average it out. So if you compute these two functions, half x, this is quarter x square plus quarter y square plus half xy, and this is half x square plus half y square. You compute the difference. Let's say you minus this from here, then what you get? This is same as 1/4 x minus y squared. So if x minus y is big, then this gets big. If x minus y is small, this gets small. So if x and y was same number, 1, 1, this replacement does not increase this function at all. But now, if those two are far apart, then now this function increase. So if we take this function as, you take the average and then square. So you have the partition, P is say B1, B2, BR. Then you take the average over this BI and then square. And then you sum it up over all I inside of R, and then you average. Then that would be our function, where as long as you saw some non-uniformity, then you break it into 2, and then this goes up. So now you generalize this to graph concept. So let's say you have V1 and V2. Let's say X and Y. X and Y. Then you take the average density. So here average is kind of density, right? So density is defined as this. So you take density, and then this is like this average, and then you take it square. And you have to add them all. Let's just say there is only these two. This is average square. And then once you break it into more, then you have these 4 parts. So before, you have one set and you break it into 2, then now you have 2 sets. But now you have a break into, say, 2 here, then it's 4 set. Then you can consider the, say, x1, x2, y1, y2, x1, xi, and yj. And then you take the square, and then you sum it up with the average. Here, average is taken by the so bigger part, this should be the weighted average. Here, this you take the half and half. But if you have a 10 number and then you divide by 2 and 8, then this must carry bigger weight because this is more of, this contributes more to the definition of epsilon regular partition. So roughly, imitating this idea, we can define such a thing. So let's make it more clear. So far it was just the intuition on why we are making this choice. So for an n vertex graph G and vertex sets xy in POG, we define this energy between xy with the density square times size of x and size of y over n square. So this is the average square as before, and this is the weight on each part. So here, this is average square, and then here both has the same size, so you take the, this is 1 out of entire 2, 1 out of entire 2. Again, here, between x and y, the pairs here is, there are n choose too many pairs, out of them this many is counted. So it's more natural to, take the x and y and then divide by n square, but this 2 doesn't really matter. N square and then n choose 2 doesn't really matter. So this is kind of still average. So we define this. And for partitions, Px and Py, this is partition of x and this is partition of y. We define Q of Px and Py you take the energy between xi and yj for all I, j inside of k and l. So this is the energy between these two parts. And then we say for given one part, its energy is between same partition. So note that we never say x and y are disjoint here. So this could be x and y could intersect each other. So now we choose this choice. And again, choice of this was, motivated from our idea. So for given partition, again, let me say again one more time. For given partition, if there are some non-regular partition here, so this is non-regular, that means there exists certain xi and y, x1 and y1 here, so that density between them is different from densities here, and then densities here, and densities here. So if these four densities are roughly same for any, then we are okay. That partition is epsilon regular. But if this is not epsilon regular, then we can find not too small set such that this red part is, not the average of these four. Then we want to break it into more, these four parts. So this becomes this four, so that now these degrees are different. So we want to do that. Every time we find the epsilon regular, non-epsilon regular partition, we want to break it further. But we want to show that we can do this until we actually obtain epsilon regular partition. And where we obtain the epsilon regular partition, we have to show that we cannot do this anymore. So we want to quantify this. Every time we do this, certain function goes up by, say, certain number, epsilon. But that function cannot go up to certain number, say 1. So it can never go beyond 1, but every time it increases by, say, epsilon, then it must terminate at certain point. So that's our strategy. So we have to come up with certain function so that if these four are different number, then once you break it, then the function goes up. And our natural choice is this taking average, so this number, and then you take squares, and then you add them with the weights multiplied it. Then, as we saw it here, in that setup, the function goes up as long as these numbers are far apart, but if they are same, then it doesn't go up. So that's exactly how we want to proceed. What kind of function that we want is exactly such kind of function. So that motivates to take the average, which is density, and then take a square, and then give the appropriate weight, and then we add. So, in order to go along with our plan, we need several things. So one of them is, when we break this, we want to show that the function never goes up. Function never goes down. We want to prove that. And then also we want to show that it not only never goes down, but if we break the non-epsilon regular part, then it actually increases by a certain amount. So those two things are necessary. So if Q refines P, then the energy of Q is bigger than energy of P. That's what we want to first show. So as long as we don't care whether we are breaking epsilon regular partition or non-epsilon regular partition, it always goes up or stay. So it will never go down. So what we do is we take X and Y in this P, and then assume that this X is further partitioned into, say, QX, which is X1 to Xk by this Q, and Y is further partitioned into Qy, which is Y1 to YL. So maybe we haven't defined what further partition is. So when we have P, which is partition of vertices, and then we have Q, which is you obtain from this P by further partition it. Then you say P is, Q defines P. To define rigorously, for each set inside of Q, it is always a union of several things in, each set in P is a union of several sets in Q. Then, it's, you say Q defines P. So let's say these are the refinements of this set X and Y. And we define G be the random variable with, let's say this is capital G. This is average density between Xi and Yj, where Ij are randomly chosen as as X is inside of Xi and Y is inside of Yj, where X is chosen uniformly at random in X, and Y is again chosen uniformly at random in the set Y. So you have X and Y, which is further partition. You choose one random vertex here, and then you choose one random vertex here, and give name X and give name Y. And this xi is the part that containing this x, and yj is part that containing this, and you consider the density between them. That's G. Then what's the expectation of this G? For each ij, what's the probability that x is in xi and y is in yj? This is the probability. And then you get this density. Then this density is same as xi, yj over the number of edges between xi and I and yj. So if you compute that, then this and this cancels out, and this is common, and then this you add them all, then you get the number of edges between x and y. So you get this is same as density between x and y. And now you compute the expectation of G squared. Then the probability that you get vertex x is inside of xi and vertex y is inside yj is this. Then you take the xi, yj density square. Then again, by the same computation, you just plug this in. Then xi, yj, xy, and here xi square y j square, number of edges between xi, yj square. Then what you know is, give me a moment. You take this out, and n square xi square xi yj eg xi yj square. This is n square x y n square xi yj density square. Okay. So each of them is same as energy between xi and yj, and you add them together, then that's the definition of energy between these two partitions. So you get this inequality. And we know that the squaring function fx equal x square is convex. So what you know is the expectation of g square is at least expectation of g square. That means this square is bigger than this square. That means if you take n square x y, you have this. So you take this and then this square and then multiply this part on both sides, and you get this. And this is same as energy between x and y. Sorry, I wrote it the other way. This. Yeah, this is bigger, so you have this. So from here, what do we know? If you consider the energy of Q, then this is same as actually this. For each part in P, you compute this, but this is bigger than the energy of P. So we have shown that this energy never decrease once you take a refinement of the partition. And not only that, we want to prove that the certain case, it actually increased by a lot, by at least certain amount. Suppose that x and y is not epsilon regular pair in an n vertex graph G, and x1 and xy1 witnesses this, meaning that you have x and y, and you take x1 and y1, then density between them is long. So this is, not within the density between x and y plus minus epsilon. It's either too small or too big. Then if you take x2 is x minus x1 and y2 is x minus y1, we have this. If you take this further partition, then it increased by certain amount from the partition before. So this will ensure that certain irregular partition, we can always improve this. We can always take a further partition so that this function increase. So in the next video we will prove this.